Hello APC Mechanics students in Unit 1 Kinematics, Class 11 Calculus Approach, Part 6, Section 1 Area under a VT Graph. We have seen previously a connection between variables of motion and analytical skills known as calculus. In addition to that, variables of motion admit another representation and can be understood graphically. So consider the above VT graph. One can calculate the area under the graph. Before I refer to the area, by the graphical representation, I mean that whenever we have a graph, we can extract certain properties, like whenever the curve is a straight line, we can directly think about the slope y-intercept or x-intercept, and this is what is meant by the graphical representation. Now, today we're gonna add another skill, which is the area under the curve. So here, we can talk about these areas bounded by this curve and the horizontal t-axis. Then the area A1, so the area of the curve would be the area A1 plus the area A2. The area A1 is a triangle of base 4 seconds and a height of 20 meters per second. Then the area of this triangle is half base times height. So half base times height. And for area A2, it's a rectangle of base 8, 12 minus 4, 8 seconds, and of a height 20 meters per second. So we can add them up. And the area is given by 200 meters. Why meters? Because the base is in seconds and the height is in meter per second. Second would cancel with this, that would be meters, and second would cancel with second, and that would be meters. So the area of the curve, basically for the previous curve, is 200 meters. As seen, the area under a VT curve has meters as a dimension. Dimension means unit. It means that this area can be interpreted as displacement, because displacement has meters as a unit. Displacement as a vector can be positive or negative. Therefore, in order to compensate for the positivity or the negativity, area above the horizontal axis is said to be positive displacement, while area below the horizontal axis is said to be negative displacement. Hence, we say that the displacement is equal to the algebraic sum of areas bounded by the VT graph only. Then whenever we have a VT graph, then the area under this curve would represent the displacement. What about the distance? The total distance is equal to the absolute sum of areas bounded by the VT curve, and let me explain myself in the following example. But first, let me introduce some formulas. The area of a square is side times side. The area of a rectangle is length times width. The area of a triangle would be base times height over 2. And the area of a trapezoid would be the height multiplied by base 1, one of the bases, plus base 2 divided by 2. So now example 2, before we get into the question, so let's look at the curve itself. Then the shape of the curve is divided into segments. Each segment is a straight line. Whenever it's a straight line, we can think about the acceleration. We can think about the slope. In this case, this is a VT graph. So the slope would be given by v over t, which is acceleration. So the slope would give us the acceleration. And another feature that we have introduced now is the area. What does the area represent? It's a VT graph, then the area would represent the displacement. And indeed, if we refer to the question, they're telling us a student plots the velocity time graph of a toy, calculate the displacement and the distance traveled by the car. Let's proceed with the displacement. So first of all, you can notice that the following curve can be divided into several segments. That would be the area A1 bounded by the curve and the horizontal axis. That would be the area A2 bounded by the curve and the horizontal axis. And similarly for A3 and A4. Now for the displacement, delta x would be the area A1 plus the area A2 plus the area A3 minus the area A4. Why? We are subtracting the area A4 because this is a negative area, which is the area bounded by the horizontal axis and the curve. So the curve is below the horizontal axis. In this case, the area A1 is a triangle of base 5 and height 4. And for the area A2, it's a rectangle of base 5 and a height 4. And for area A3, that would be of base 5 and height 4. Whereas we're gonna now subtract the area A4, as mentioned here. And that would be of base 5 and height negative 4 or 4. And the displacement in this case would be 10 meters. Now, this is part of the question. The other part would be to calculate the distance traveled by the car. Then in this case, so the total displacement is 10 meters. What about the area? It's exactly the same, but we're gonna add the absolute sum. So this would be switched to positive, and the answer in this case is given by 60 meters. So from a VT graph, by referring to the area under the curve, we can calculate the displacement or the distance traveled by moving object. then the total distance is 60 meters. Now section 2, tangency and its slope. This is a very important section. The tangent to a curve is a straight line that touches the curve in one and only one point. So basically this is the function, which is the curve in blue, and the tangent to this function at this particular point is given by this straight line, and notice that it touches the function in only one point. That would be the point of tangency. And a convenient way to understand the tangent is to recall the tangent through a circle. So the tangent to a circle is a line that meets or intersects the circle at a single point, and that would be perpendicular to the radius. In fact, the slope of the tangent to the function is equal to the derivative of this function. So let me repeat that. So now we know what is a tangent. The function, the tangent is a straight line, and whenever we're talking about straight lines we think of slopes. Then the slope of the tangent to the function is equal to the derivative of this function. Why the derivative is important? Because we know that the derivative is a mathematical operator that links variables of motion to each other. Before we do the linkage between physical quantities and the graphical reading, we need to study the sign and the variation of the slope of a tangent. We know that variables of motion are partly vector quantities, and whenever we're talking vector quantities, we're interested in the sign and the variation, etc. So the first thing to keep in mind is that the slope will be linked to a vector quantity, so that the slope has both direction, which is the sign, and a magnitude, which is the value. The graphical reading is a crucial technique and it reveals certain characteristics related to physical quantities. Then let's kick things off by analyzing the slope of a tangent. Let's start by the sign of the slope. Now here we have the same function, and we have three different tangents. This is a tangent at this point, this is a tangent at this point, and this is a tangent at this point. We need to identify the slope, or the sign of the slope. In the first one, the slope is negative because the line is pointing downward. In the second one, the slope is 0. And here, why I mentioned that this is an extremum point, because the slope of the tangent is equal to the derivative of the function. And if the slope is 0, which means that the derivative of the function is 0, and we know that whenever we derive the function and set it equal to 0, we're searching for extremum points. Alright, now for the last one, the slope is positive because the line is pointing up. Now this is regarding the sign. Now what about the variation? Now I'm considering this interval of the function, and here in this animation we have animated the tangent of the slope from during this interval. Okay, so in this case the slope increases. Why the slope is increasing? How can we understand that the slope is increasing? One way to do that, if you imagine the animation, you can think of it as if the slope is rotating in this direction counterclockwise. So as if the line is rotating in this manner. In this case, the slope of the tangent to the function is increasing. Now what about this function during this interval? Now notice carefully the animation. The line is rotating in this manner. We say that the slope decreases. You can think of it as if the slope is rotating in this direction, which is clockwise. So whenever you try to imagine the slope of the tangent along a certain interval, if it's rotating in this direction counterclockwise, opposite to the motion of the clocks of the hands, this means that the slope is increasing. And if it's rotating with the clocks of the hand in this manner, then the slope in this case decreases. Okay, let's consider this function. Let's consider the first interval indicated by a and b. If you notice that carefully, the slope is varying in this manner. First of all, we need to discuss the sign of the slope. The slope in this case, it's always pointing down, then it's negative. What about the variation? It is increasing. Now, if you consider the another interval, which is BC, the line is pointing up, then the slope is positive. Now, what about the slope of a line? As if it's rotating in this way, which means that its variation is increasing. Now we have this function. We will consider this interval. The line is pointing up, so the slope is positive. You notice that it's rotating in this manner, then the variation is decreasing. Now what about the other segment? In this segment, the slope is pointing down, so it's negative, and its variation would be decreasing because it's rotating in this manner, clockwise. Now what about this function? You notice that the slope during this interval, it's always pointing up, so the slope is positive. What about the variation? It's rotating in this manner, then the variation would be decreasing. Now what are the takeaways for section 3? Remember that if the slope is pointing up, then it's positive. If the slope is pointing down, then that would be a negative slope. Slope varying in a counterclockwise manner, then its variation is increasing. Slope varying in a clockwise manner, that would be a decreasing slope. And the slope of the tangent is equal to the derivative of the function. And at this point, we can summarize all the graphical interpretations that we have put forward from the beginning of the unit. Then the direction of velocity, or not only for graphical analysis but also related to the motion. So let me say direction of the velocity is related to the direction of motion. So velocity gives us motion. A and V, same direction, that means speeding up. A and V, opposite directions, means slowing down. Velocity V is positive, means the position increases. Velocity V is negative, mean position decreases. A is positive, mean velocity is increasing. A is negative, means velocity is decreasing. Notice that if the velocity is increasing, it doesn't mean that it's speeding up. Okay, so to know whether it's speeding up or slowing down, we need to look at A and V at the same time. Slope pointing up means the slope is positive. Slope pointing down means slope is negative. Slope varying in a counterclockwise manner means slope is increasing. Slope varying in a counterclockwise manner, in a clockwise manner, slope is decreasing, and the slope of the tangent is equal to the derivative of the function at that particular point. Now exercise 1, the graph shows the position x as a function of time of an object in linear motion. Which of the following graphs best represent the velocity v of the object as a function of t? Then we have an xt graph. All the choices shows a vt graph. You need to associate one of the choices with the given xt graph. Then the best way to do that is to divide the function into intervals according to the variation. Here we have an increasing function, then we have a decreasing function. We're gonna divide it like this. So that would be the first interval, that would be the second interval. In the first interval, the position is increasing, which means that v is positive. And in the second interval, the position decreases, which means v is negative. And notice that at this point, the position remains unchanged, which means this is a zero velocity. The object is not moving anymore. And this is reasonable. Why? Because if we're going from positive value to negative value continuously, we need to pass through zero. If we're going from 5 to negative 5 across all the values, at some point we'll pass through the zero. Now, so let me repeat and say we're going from positive to negative. This is from negative to positive, so this is excluded. This is from negative to positive, also excluded, as well as this. So we're left with A and E. A would be the correct answer, and let me explain why. Because during the first interval, it's almost a straight line, which means the slope is constant, and we know that in this case the slope represents x over t, which is the velocity, which means that along this interval almost the velocity is constant, which agrees with A, before dropping down to zero. Now exercise 2, students are studying the motion of an object that is moving in the xy plane. The x and y components of the object's velocity vx and vy respectively as function of time are represented by the graphs shown above. Which of the following is a correct claim about the x and y components of the acceleration of the object and provides correct evidence to the support of the claim? Now we have vt graph, and at this point we know that we have so many tools in order to analyze a graph. In order to know what tools we should use, we need to refer to the choices. And the choices, they're talking about the acceleration. So if you look carefully, v over t, which represents the slope, that would be the acceleration. So basically we need to refer to the slope of each curve, which is a. They're talking, if you look carefully at the choices, they're talking about the sign of the slope. So we need the sign. We're interested in the sign. And we're interested in the variation as well because they're mentioning whether it's increasing or decreasing. So let me say that also we're interested in the variation. Let me say this is graph 1 and this is graph 2. For graph 1, let's discuss the sign of the acceleration. So notice that if we let me draw tangents at different points. So notice that the tangents are pointing upwards, which means that the slope is positive, and they are rotating in this manner, which means that A is increasing. So this is for the x-axis. And for the y-axis, which is graph 2, you notice that the slope is the line itself, the tangent. So the acceleration is negative, it's pointing down. And in this case, the acceleration is not varying because the slope for a straight line is constant and can be determined through any 2 points. So A is constant. That would be for graph or the y component. Now for the first choice part A, x is positive and AY is 0. This is wrong because if the slope is 0, that would be a horizontal line, but this is not a horizontal line, this is a line going downwards, so choice A can be directly eliminated. B, AX is positive and increasing, this is true. And AY is negative and constant, so we're gonna look at B. AX is positive and increasing and AY is negative and constant, which is the same, we're gonna look at C. D, AX is positive and decreasing, this is wrong. AX is positive and decreases, this is wrong. However, statements or choices, we need to choose the correct answer with the correct evidence, because for the two statements the evidence will change. Let's start with part B. They're telling us because the slope of Vx is positive. Indeed, we've said that Vx is positive and increasing, that's true. And the slope is Vy is negative and constant, so B is correct. However, for C, they're talking because the values of Vx, we didn't interpret the values of Vx. We have interpreted the slope of each curve. For this reason, B is the correct answer. Exercise 3. An unstretched ideal spring hangs vertically from a fixed support. A 4.0 kg object is then attached to the lower end of the spring. The object is pulled down to a distance of 0.35 meters below the unstretched position and released from rest at time t is equal to 0. A graph of the subsequent vertical position y of the lower end of the spring as a function of t is given above, where y is equal to 0 when the spring was initially unstretched. At which of the following times is the upward velocity of the object is the greatest? So okay, in this unit we didn't discuss such type of motions or graphs that has to deal with sinusoidal motion. This will be interpreted at unit 6. However, it's good here to try to understand what's happening. I'm telling you that the velocity in such type of graphs is the greatest at these points. So here the velocity is the greatest, as well as here, okay, at these points. Why? Because the velocity would represent the slope of the YT graph, and if you look carefully, the graph is the steepest at these points. They will have the greatest slope going up compared to all other points. So these points would represent the points of greatest velocity due to the interpretation of the slope of the YT graph, which is the velocity. They're talking about the upward velocity, which means the velocity should be positive, the line should be pointing upward. Now at 0.25, so at 0, no, it's not this. At 0.25, let me see, so this is 0.5, and that would be in between 0 and 0.5, so this is 0.25, then the correct answer would be B. At C, which is 0.5 here, no, here the slope is 0, so the velocity is 0. At 0.75, which is here, it has the greatest speed, so but not the velocity, because the velocity would be pointing downward. At 1 second, the velocity in this case would be 0, so the correct answer would be B. Now exercise 4. An object is moving in the x direction as shown in the graph. At time t is equal to t1, the motion changes. Which of the following describes the velocity v before and acceleration a after time t is equal to t1? Then they have split the graph according to t1. Before t1, we need to discuss the velocity according to this table. And after t1, we need to discuss the acceleration, and this can be done by referring to the slope of the xt graph, because x over t would represent the velocity. Now this is 1 and that would be 2. For the first one, what do we have? The position is increasing, that v is positive, And what about the variation of the velocity? It's a straight line, then v is constant. For the second interval, the position is decreasing, which means velocity is negative. However, if you draw tangents at different points, we're gonna notice that the slope is trying to rotate in this manner, which means that v is increasing. But if v is increasing, which means that the acceleration is positive. So velocity is positive, acceleration is positive, and by that the correct answer would be C. Exercise 5. Cars A and B are moving in opposite directions along a straight road. They pass each other at the time t equal to 0. So at t is equal to 0, they're gonna pass each other. Car A has a positive velocity, which means it's moving in the positive direction. So let me draw here something. So car A will be moving like that, and car B will moving like that because the velocity is negative. The distance between the cars at t is equal to 8 seconds, so we're interested in the distance. Now, if you look at this graph, you can directly think, because they are straight lines, we can think about the acceleration, but we're not interested in the acceleration. However, because it's a VT graph, we can calculate the displacement. We are interested in the separation distance between two cars. If car A have been displaced a certain distance to the right and car B have been displaced a certain distance to the left, then the separation distance would be the displacement of car A plus the displacement of car B. So the displacement of car A would be 8 multiplied by 12 divided by 2. So that would be 8 multiplied by 12 divided by 2, and that would be 8 times 6. And 8 times 6 would be given by 48 meters. And now for car B, the displacement would be also 8 times 12, or negative 12, because this is a negative area. That would be negative 48 meters. But the thing is that we should add 48 plus 48, and that would give us what, 96 meters, because we are talking about the separation distance between the two cars, and the correct answer in this case would be D. Exercise 6, which is the final exercise for this video. The position acts as a function of time for an object moving in a straight line is shown in the graph above. Which of the following best describes the object's speed and direction during the time interval D? So we know that the direction is related to V, speed is related to A and V. So we have an xt graph, so basically we need to understand the variation of the slope. Now if we draw tangents at different points, so we notice that at each point the slope is pointing upward, so V is positive. The slope is rotating in this manner, so it's decreasing. V is decreasing, which means A is negative. So A and V have opposite signs, which means that the speed is slowing down. So we are slowing down, or the speed is decreasing. So we are interested in either A or D, but the direction of motion is dictated by the velocity. Velocity of positive, so we're in the positive direction of motion, and that would be wrong. Then that's it for me in this video, guys. See you soon and a new one.